Hi, in this video we are going to talk about the theoretical basis of graphs, Hamiltonian cycles and Eulerian cycles. So let's get started. There are two main types of graphs, the so-called undirected and directed graphs. As you can see in this illustration, this is a typical undirected graph, which means that you can get from, for example, A to B, and you can get from B to A. And there's another type of graph, the so-called directed graph. In this situation, for example, each edge has a direction. I mean that, for example, in this situation, you can get from vertex A to vertex B, but you are not able to go from vertex B to vertex A. And we can model, and that's what we are going to do, we can model the undirected graphs with the help of directed edges. How? You just have to direct an edge from A to B and another edge from B to A. And if you do this, then you can get from A to B because there's a directed edge from A to B, and you can get from B to A because there's another directed edge from B to A. So this is the two main types of graphs. And I would like to talk a bit about Hamiltonian path and Hamiltonian cycles and Eulerian path and Eulerian cycles. It's going to be very, very important, and we are going to be a bit more specific when we are going to talk about the traveling salesman problem. So it is a path in an undirected or directed graph that visits each vertex exactly once. It's very important that we have to visit it exactly once. So Hamiltonian cycle is a Hamiltonian path that forms a cycle. And determining whether such paths and cycles exist in graphs is very, very hard. It's a typical NP-complete problem. So we usually, we don't want to calculate the exact solution, and that's why we usually make simulations, the so-called simulated annealing or genetic algorithms becoming very, very popular, even in the 21st century. And for example, the greedy neighbor search, where we go from node to the nearest neighboring node, and it turns out to be quite efficient because it's not NP complete. We can do it in polynomial time, and the solution is rather good. So why is it important, the Hamiltonian cycles, why we are talking about it so far? For example, in this situation, we have 4 vertices and 4 edges. And in this situation, it's quite straightforward how to form a Hamiltonian cycle. And as we have discussed earlier, we visit each vertex exactly once. So the starting vertex is A. We go to B, we go to D, we go to C, and we go back to A. And we can easily construct graphs where we cannot do it so easily. So there are situations where Hamiltonian cycles, we are not able to form Hamiltonian cycles and construct them. So why is it important? Because the traveling salesman problem relies heavily on Hamiltonian cycles, and lots of graph algorithms can be reduced to traveling salesman problem. For example, optimization problems and so on. So what is this TSP or traveling salesman problem? We're given a list of cities and the distances between each pair of cities. And what is the shortest possible route that visits each city exactly once and returns to the origin city? And we can come to the conclusion that if there is a Hamiltonian path for a graph and a Hamiltonian cycle, because we want to get back from where we have started, it is the solution for the traveling salesman problem. So if we can get the Hamiltonian cycle, then we get the solution of this traveling salesman problem. And because finding the Hamiltonian cycle is an NP-complete problem, finding the solution for the traveling salesman problem is also NP-complete. There's another chapter where I'm going to talk about a bit more about traveling salesman problem. Why is it important? What are the applications? And in this section, we are going to implement it with the help of simulated annealing. And why is it good? because we are not going to get an exact solution, the best solution, but we are going to be able to solve this problem in polynomial time and get an approximate solution, which is very, very good. So that's about the Hamiltonian path and cycles. Let's talk a bit about Eulerian path. It is a trial in a graph which visits every edge exactly once. So what's the main difference between Hamiltonian and Eulerian path? That Hamiltonian path visits each node, each vertex exactly once, and Eulerian path visits every edge exactly once. Eulerian cycle is an Eulerian trail which starts and ends on the same vertex. An undirected graph has an Eulerian cycle if and only if every vertex have even degree. The degree is the number of edges that's coming out or going in to this vertex. And we can construct graphs that has Eulerian cycle with Herholzer algorithm. And it's very important for the Chinese postman problem. What is this problem? A postman needs to go through every street at least once, and he wants to make the circuit closed and wants to find the shortest path, of course. And it has lots of applications. And if there is an Eulerian cycle, there's a solution for the Chinese postman problem. So these are the main problems. I mean, so why is it important, the Hamiltonian cycle? Because we can reduce the traveling salesman problem to this the solution of the Hamiltonian cycle. And why is it important to solve the Eulerian path? Because we can solve the Chinese postman problem. We can reduce the CPP problem to finding the Eulerian cycle. So that's all what I was going to say about this topic. And in the next chapter, we are going to talk about more, especially about the traveling salesman problem, because it has several applications in real life and optimization. Thanks for watching.